So, shall we start? Yep. Okay, hi everybody. We ended up here last time, right? So we ended up doing the forward pass through the MLP. So a quick recap on what we did. So what was the MLP? The MLP was a kind of, vanilla. Is it working or? Yeah, it's working. So MLP was the sort of vanilla deep neural network, right? So the one which you can think of. So it gets your data, it's going to do a fine transform on it or a linear transform on it, and then it does activation, then again does another linear transform, activation, and so on until you get to the output, right? So that was the MLP, and we said like, this is a kind of feed-forward neural network because you feed your data, it's going to go forward always. There is no recursion inside your architecture, so that was a deep feed-forward neural network. And what we wanted to do with that guy, we wanted to do two things. First of all, we wanted to know that if somebody gives us this neural network, which is already trained, so somebody tells you, I have trained this neural network, so it's perfectly working for your job, then you want to give one input to this guy, and then this input going to flow over the neural network, going to give you the output, right? And we call this, what was this process? What do we do with this neural network when we pass one data forward? It was inference, right? So you're doing inference, you just give your data, it's going to give you the predict. It's going to tell you what is the label, right? So that is inference, and to do that, we call this forward computation, we called it forward pass, right? So this was forward propagation on forward pass, and the whole idea was pretty easy. So you start with your data, and you always just multiply it with a matrix, so it was the linear transform. You're going to get something, we usually show it by Z, and this guy is the non-activated version of your first layer output, and then it's going to get activated with the activation function. Now you have the activated one. Then this guy is going to play the role of the input for the next layer, right? And then you're going to just multiply it with another matrix. You get the next unactivated version of the hidden features or hidden information, and then you again activate it by activation function, and you keep on going till you get to the output layer. So this was the whole idea. We have L different layers. We just forward pass it, meaning that we just compute this linear transform, and we activate every single entry inside the transform. And once we did that, then we are basically done with the forward pass. So we are over with the whole forward pass when we finish with all the layers. And what do we collect at the very end? All the activated and non-activated outputs of every single layer, right? And I told you you need it when you want to do backpropagation. We are going to do the backpropagation today, okay? Now, one question, what is the thing that we need to learn in this architecture? Weights, right? All of those matrices, W1 to WL plus 1, right? All of those matrices, every single entry inside them, we need to find out what they are. We need to learn them. What do we do to learn them? We minimize the empirical risk. What algorithm do we use? Gradient descent. So what does it mean? What do we need if we want to update? The gradients, right? So we need to be able to compute the gradient. So the whole thing that we need to do is that we need to be able, once we started from the information from the input layer, and then we pass everything forward, we computed everything, then we need to be able to compute the gradients, and this is the whole trick. This is the whole challenge now. And then we're going to do it with backpropagation. To be able to do that, let me just do a bit of compact representation here. So this is the neural network. Right now, you do understand that every single layer here in between two consequent layers, it's simply a matrix, right? So it's a matrix multiplication. You can look at every layer as a vector getting multiplied with a matrix and activated. And we typically use this diagram because this is more compact. And as you're going to see, it's going to be easier to do the computation on that one. So this is a kind of compact diagram, so you can look at it here. X is the whole collection of the inputs you have. It's going to get multiplied with one matrix, so basically it collects all of these links in between. And then you're going to get the first activation. And then out of that activation, you have some activated output. You're going to do again linear transform activation and so on until you get to the output. So when you look at this diagram, what you should pay attention to, first of all, the thing that you should pay attention that this W is collecting all of those weights, right? So it's a matrix. It could be of different size, so different number of rows, different number of columns. We talked a lot about this, how you can count the number of rows and columns. But in general, this is a matrix. It could be a rectangular matrix. And it's representing everything, every weight you have inside that layer that you need to learn. And then once you multiply your previous input to this guy, to this weight, then you're going to have one particular output. This is the Z1, the one which I show by Z. And this is not yet activated, right? So that Z has not been activated. It's just a linear transform. And then the only thing that you do, you're going to just pass that Z simply through every single entry is going to pass through that particular function, right? So it's an entry-wise function operation. And then you're going to have Y at the output. Now you want to go for the next layer. If you remember, we had this one dummy thing. So one extra 1 we put on top of that Y. And then this guy again gets multiplied to the next weight, activated, and so on, right? Just to recap what we are doing, right? So you can think of the whole neural network now like this graph, and this is going to be very helpful. Okay? Everybody's clear? Okay. Then, so yeah, this is quite important when we want to do the backpropagation, and then let's just go ahead and then start with the idea of training. Okay? So now, what is the idea of training? As I told you, the whole idea is that you compute the empirical risk, right? So meaning that you're going to get every single data point inside your data set. You pass it through this architecture forward, doing whatever we did on Tuesday. So for every single of them, you put it at the input of your neural network. It's going to pass forward. You're going to compute the output, right? Then you're going to compare this output to the true label, which you have inside your data set. This is one sample loss that you get, right? And then you need to compute all of these sample losses inside your data set, and then you average them, right? So this is going to be your empirical risk. So the whole thing that you need to do is to just compute those sample losses and try to find out how to minimize them. We do know that we need to compute the gradient of that empirical risk, and then we just move in that direction, not the gradient itself, but negative of the gradient. But at the end of the day, we do know what is the computation, right? So we need to define the loss, and then just use gradient descent to train it, meaning that we want to just minimize that empirical risk that we compute. And the whole challenge now is that we want to compute the gradient. And as you know, as I mentioned a couple of times, we want to compute the gradient, meaning that we want to compute the partial derivative of that empirical risk you computed with respect to every single weight that you have in this very deep architecture, right? So with respect to every single entry in every single of those matrices you have in your architecture, you want to be able to compute all of those partial derivatives. And this sounds quite complicated, but as we're going to break it down, it's not. You can simply develop one simple algorithm which does it for you. And that algorithm is what we call it backpropagation. So one thing from my side, don't say ever that I am training my neural network using backpropagation, or backpropagation is training my neural network. Backpropagation doesn't do training. Backpropagation simply computes the gradient for you. Gradient descent is the one who is doing the training, right? So backpropagation is simply an algorithm which helps you compute the gradient with respect to all of those weights very efficiently, okay? It's not an optimization algorithm, right? So many people say that. I do know, like if you open up any, like these videos online that people want to talk generally about deep learning, then they usually come to say that, yeah, we use backpropagation to do the training, but this is not a correct argument, okay, if you are very precise. So backpropagation is simply an algorithm which helps you compute the gradient. And let's see what is backpropagation. Okay, so let's get back to our problem. So the whole problem of training, as I told you, you have your data set. So here inside your data set, you have x. X is the sample, right? The thing that goes inside your neural network, right? And then once you pass x, you're going to get one output, right? And then that x is labeled by v, okay? And for now, I mean, since we're thinking about the general thing, we can assume that this v itself is also a vector, right? So we're going to see that in general. I mean, for classification, for instance, it's just an integer. But in general, I mean, you can think of it to be a vector as well, okay? So what I do know that when x goes inside my neural network, I do expect to see v at the output. But what's going to happen if I do forward pass? So if I pass it forward, so this guy you see here, pass f, so forward pass. If you pass it forward in your neural network, so this x is going to get multiplied and activated over and over, and at the very end it's going to give you y, which is not necessarily the same thing as the v that you have, right? And I'm going to show it like this, just for a couple of slides. Pass f, x given w, and that w is simply the weights that you use when you were passing forward. So it means that this vector w is just collecting every weights that you had in all of those matrices, okay? So it's a very, very long vector in general, collecting lots of weights. Now, if you fix that, then all of those matrices are fixed. X goes in, you can compute y, correct? Right? Okay. So y is computed, and then this guy, x, is supposed to have the true label v, but you are seeing y. So what you're going to do, we talked about this before, we are going to compute the loss. So L here is the loss function. We are going to compute this loss between the output y and v for every single b, for every single data that we have inside our data set, and then we average all of them out, right? And we want to minimize this guy. And how are we going to do this minimization? We're basically going to use gradient descent, right? But before doing that, I am showing here the empirical risk to be a function of weight w. Can you tell me where is this w? Where is the w hidden in this whole expression? What guy contains w? Y, correct? So y is the one who is containing w, correct? So y is the guy who contains w. If I change w, y is going to get changed. So y is a function of my weight, right? So y is here, and then I want to compute this guy, right? And or minimize this guy. And if I want to do that, this means that this very complicated function that I do have, I need to compute the gradient of this very complicated function with respect to the weight. This is a very long gradient vector. And then I start from one weight, so I set my weights to be something. Now the weight is fixed. I compute the gradient. Once I compute the gradient, I update my weight as the previous weight minus learning rate times the gradient, right? It's now a new weight. Then I get that new weight, and then again I compute the gradient at that new weight, and then again I update my weight as weight minus learning rate times gradient, the new gradient. And I keep on repeating till the algorithm converges. So the whole thing is that I do know if somebody fixes the weights for me, how I can compute the gradient at that particular weight, right? If I do know how to figure this out, then I can do the gradient descent. Clear? Okay, so let's look at it. I mean, in general, we want to compute the gradient at a given fixed weight, set of weights, and then this is the whole challenge. So it sounds to be very challenging, and then let's start with breaking down the whole equation and see what is inside that, okay? So first of all, let's just recap what is inside W. I do know that all of you are seeing it right now, but just to recap. So this guy, W, is like I mean by this W? I mean that I go in the first weight matrix, I get the first column, put it here, the second column, put it under it, the third column under it, and so on till the first matrix is over, okay? Then I go for the second matrix, I put the first column under everything, second column under everything, and so on. So you're going to see that this is a huge vector, right? So first layer, all of the columns, second layer, all of the columns, and so on till the last layer, all of the columns, right? And every single of those W's here itself is again a vector of all of, I mean, it's a column, right? Column vector. It's containing lots of weights, right? So at the end of the day, what you can think here as W is that this vector is containing all of those weights that you have inside these matrices. So you just do an increment, you start from the first weight, and you're going to write them down under each other, right? Now, if I want to compute the gradient of r hat with respect to this long vector, what should I do? How do I compute the gradient? Or now, not how I compute, what is the definition of the gradient? It's gonna be exactly the same length vector, right? And every single entry is going to be the partial derivative of your empirical risk with respect to that particular weight, right? So your gradient is going to be of this form. It's going to contain all of these guys, right? Correct? So you see it? So I hope that you are seeing what I'm doing, right? So it's very just notation, very basic right now, yeah? So I want to be able to compute the partial derivative of the risk that I have, the empirical risk, with respect to any particular weight inside my architecture. So you just point to this weight. So we say the weight which connects the third neuron to the, in layer 1, hidden layer 1, to the, I don't know, fifth neuron in layer 2. Okay? And then I need to be able to just compute the partial derivative of my empirical risk with respect to this guy. And what does partial derivative mean? It means that if everything is fixed in this architecture and that particular weight changes slightly, I want to know how does the empirical risk change. Yeah? Everybody's clear? Okay. So, oops. No. Sorry. So I want to compute this guy, and if I open it up, so this r hat is simply the average of those losses, right? And once again, this weight is going to show up somewhere inside this y, right? Because this y was computed using that weight and lots of other weights, right? So I want to compute this one. First of all, can I take that partial derivative, this guy, inside summation? Yeah, I can do it, right? Derivative of a summation is summation of derivatives, right? So I can simply write it down in this form, correct? Right? Now, since I can write it down in this form, what can I conclude from this? I can conclude that if I do know how to compute this gradient for one pair of sample and label, then everything is over. Because I have this label, sample and the label, and compute that gradient, and I change them, compute again the gradient, and so on. And once I have all of those gradients, I average them, right? Correct? So for every single sample that you are you compute, if you are able to compute this gradient or this partial derivative, your final gradient that you are looking for, it means that the gradient of your empirical risk is going to be average of those gradients, right? So you might have heard of this, that the gradient that you are looking for is the average of sample gradients. And by sample gradients, we simply mean these guys. Okay? The gradient of your loss when you think of one sample only. So the whole problem is that I be able to just consider one single data point and its label and be able to compute the partial derivatives of the loss function, or what we call its sample gradient, for that particular sample point. And if I can do that, then I can do it for every single guy inside the data set, and then the average of them is going to be my gradient of the empirical risk. Everybody's clear? Yeah? Okay. So up to this point, nothing is specific. So this is why from now on I am going to drop that index B in all of the formulations. So from now on, you always think that my whole data set contains one pair of data and label. Because basically, if I can do this, I can generalize it to any data set, correct? So I am going from now on to think of one single data point x, and it's labeled v, and then I'm going to write down this expression, which is showing you explicitly how your output or how the sample loss is depending on your weight. I'm going to drop it and write it down in this compact form. So instead of pass forward of x given the weights, I'm going to simply write y. But you do know that y is a function of weight, right? So it means that if I take the derivative of y with respect to weight, it's not simply 0, right? So it changes. So I'm going to do that now. And the whole thing is that I be able to compute this gradient, this final term that I want to do it, right? And now, if you look at this, you're going to see that this y is basically a nested function of all of the weights. And what do I mean by nested function? It means that maybe y is not a function of that weight immediately. So it was not the weight of the last layer, but it was the weight of the second last layer, right? So y was a function of the output of the last layer, the second last layer, right? And then the output of that second last layer was a function of that weight, right? So it's an idea of nested functions. So something is not an immediate function of that thing, but is a function of that thing. And all of you had this idea in high school, right? So let's just quickly recap on that idea of nested function and see how we can compute the gradient for those nested functions. Once you see it, you're going to see how the backpropagation algorithm works. Okay? Any questions? Everybody's clear? Yeah? Great. So now let's look at this idea of nested functions. So what, as I said, nested function simply means that something is a function of something which is a function of something, right? So for instance, y is a function of z, right? And z itself is a function of x. Then I'm going to say y is a nested function of x, right? Because if I change x, still y is going to change, right? But it's not immediate. I mean, x is going to change z, and z is going to change y, right? OK. Now, let's look at this one. Let's do this together. So what I want to do, so this y, as I told you, is a function f of z. And z itself is a function of x, right? And now what I want to do, I want to be able to compute dy to dx. I want to just compute the derivative of y with respect to x. And I do know all of you had seen it before in high school, but I want to do it in the way that we just talked about derivatives, because this is going to help you all the way along this course and any other course, any other thing that you deal with computation when you think of derivative in this form. Okay? Now, if I want to write it down, you remember that we talked about this, that I told you if y is a function of x, then derivative for us, it simply means that if I want to change x very, very slightly, so very tiny bit dx, and I want to know how does y change, then I'm going to multiply the derivative of the function to that change, right? So we said that this is f dot x times this guy, right? So that was the idea. Now, here, if I change dx very slightly, okay? So, sorry, x. If I just change x very slightly with dx, how does y change? How can I write dy? It's going to be the derivative of this whole nested function with respect to x times dx, right? So this is going to be the whole derivative of f g x, correct? Now, let's use this kind of idea to compute that derivative of the nested function with respect to x. So how can I do this? I can first say that, OK, let me just look at this first function where z is a function of x. Now, if I change x slightly, so if I change x with dx, then what's going to happen to z? I can simply compute the change in z in this form, right? The change in z, dz, is going to be derivative of the function g times dx, right? Now, next thing, if I change in the second function, where y is a function of z, if I change z slightly, very slightly, dz, how gonna y change? It's gonna be the derivative of that function f at point z times dz, right? So dy is going to be the derivative times dz, right? Now, dz itself is given in this form, right? So I can just replace dz with this expression, g dot dx, correct? Can I do that? OK, I'm going to do that. So this means that dy is derivative of f at point z times derivative of g at point x times dx, correct? And I wanted to now, look at the board, I wanted to know how does y change, what is dy, when I change x slightly with dx. So that was the derivative. And you have it now in the slide, right? So that expression here, this expression here, f dot g dot, is the derivative. This is what you know it as the chain rule, right? So you could simply say that if I think of, I do see here that dy is f dot g dot times dx. And I do know that dy can be expressed as the derivative of this nested function times dx. So what I conclude that the derivative of this nested function is the derivative of f at point z times derivative of g at point x, correct? Everybody's clear? So this is the chain rule, which you had it in the high school. And you can simply extend it to a general case, right? So here you assume that z1 is a function of x. And then you have z2, which is a function of z1. And then z3, function of z2, and so on till you get to zn. And then you compute your output y. How do you write down the derivative? Don't look at that expression. Just try to do the chain rule. So if I want to compute dy with respect to dx, what can I do? I do know that y is an immediate function of the last zn, right? So is it zn or zn plus 1? Zn. OK, great. So how can I do it? How do I write it down? So I do know how to compute dy with respect to dzn, right? I can't take the derivative with respect to zn because it's an immediate function, right? So I can compute dy to dzn. And what should I write next? dzn dx. Great. Now, again, zn is not an immediate function of x, but it is a function gn, I guess. Is it gn or? Oh, yeah. Gn of zn minus 1, right? How can I write down this guy now? This guy. dzn to dx. How can I write it down? dzn to dzn minus 1, which is the immediate term in the function, times dzn minus 1 to dx. And I can again open this guy up, right? It's going to be dzn minus 1 to dzn minus 2 times dzn minus 2 to dx. And I keep on going till I get to dz1, which is the immediate function of x, correct? So this is exactly what you have here. So dy to dzn, and then dzn to dzn minus 1, and so on till you get to z1. And then dz1 to dx you can compute because z1 is an immediate function of x. Everybody's clear? So this is the idea of chain rule. And basically what it says that when you have a function which is a nested function, then the derivative is going to be the product of every single derivative, right? Every single immediate derivative, correct? So that is the chain rule. And one cool representation of the chain rule is by using something that we call it the computation graph. And this computation graph is very useful because it's going to make everything schematic and you simply understand it. So you can think of x passing through some function. So that g that you see on the edge is a process, is a function. So it's going to get x, going to give you the next variable z1. And z1 is going to just get passed through g2 and going to give you z2. And so on till you get to zn, and finally zn pass through function f and you get y. Right? So if you want to compute y, you need to do a forward pass, right? You put x, then you compute z1, then you compute z2, and so on till you get to y, right? And now let's look at the chain rule and see how we can compute the derivative in this case. Okay? So if I want to compute y, I told you, you just do a forward pass. You start with the value here, and then you compute z1, and out of z1 you compute z2, and so on till y. And now say you want to compute derivative of y with respect to the input x. How you can do it? You can just use this chain rule that we had, right? So the first thing that you would do, you would say, OK, I need to know the derivative of y with respect to zn, which is f dot, right? The derivative of the immediate function. And if I do know that, then from that point, I just need to know the derivative of zn to the input, right? Again, you get to zn, and you would say, OK, if I want to just compute the derivative of y, for instance, with respect to, I don't know, zn minus 1, how can I compute it? So I would say y derivative with respect to zn times the derivative of zn with respect to the previous one, right? Correct? And if you keep on going backwards, you're going to end up with the very last guy. So you're going to end up to this point, for instance. Derivative of y with respect to z1 is going to be derivative with respect to zn, then zn to zn minus 1, then zn minus 1 to zn minus 2, and so on till z2 to z1. So you're going to end up here. And now if you want to compute the derivative of y with respect to x, you're going to get all of those products. You multiply it with the last chain, and you're going to get the derivative with respect to x. Everybody's clear? Yeah? OK. So if everybody's clear, let's try to have one example. So let's consider this particular example. OK? And now, what is in this example happening? We have one variable x, which you can choose to be some number. And then once you fix x, then you're going to have z1, which is 2 times x. And then you have z2, which is z1 squared. You have z3, which is exponential function of z2. And finally, you have your output y, which is log of z3. Okay? First of all, before going on, just let's see how I can write down y in terms of x. How can I write down y in terms of x? Y is log of z3, and z3 itself e to power z2, right? So what is log of exponential of z2? z2 itself, right? So y is log of e to power z2, which is z2 itself. And what is z2? z1 squared. And what is z1? What is it? 2x. So it's going to be 2x squared, right? Correct? Which is going to be 4 x squared, correct? So if I am doing high school math, I'm going to write immediately y equals by 4x squared. And then what is the derivative of y with respect to x? What is it? 8x, right? Great. So I have 8x, and whenever you fix x for me, I can tell you what is the derivative of y with respect to x at that point, right? So if you put it half, it's going to be 4, right? But your computer cannot do this. Your computer doesn't work with symbols, right? It works with numbers. So on your computer, z1, z2, z3, all of them are variables which upon fixing x, they are going to be fixed, right? And then the whole thing that you need to know is how I can just write down an algorithm which, given x, it could be able to end up with this value of 8x or 4 in our example. So how does your computer work? Your computer works like this. So it's going to say that this variable x is depending on z1 2 times that x, right? Correct? And then z1 is connected to z2, z1 is squared, right? And so on till y. And now, if you want to compute y, your computer is going to really do a forward pass. So it's going to fix x to be half. Then it's going to see z1 is 1. Then 1 squared is 1 again. 1 e to power 1 is e, and log of e is 1. So your y is 1, right? So your computer is going to do all of these 4 operations to compute y, right? And now you want your computer to compute the derivative of y with respect to x. How can you do this? Well, you can just, once you are defining these forward functions, you can also define the backward functions, right? So once you know that z3 depends, or sorry, y depends on z3 as log of z3, then what would be the derivative of y with respect to z3? What is it? Derivative of log is 1 over the argument, right? So it's going to be 1 over z3, right? If z3 is a exponential function of z2, then the derivative is going to be, again, exponential, right? If z2 is z1 squared, then the derivative is going to be 2z1. And if z1 is 2x, then the derivative is going to be 2, right? So you can have forward functions and you can have backward functions, right? You can define it on your computer. And now, how does your computer work? Your computer does know, I mean, your computer did this forward pass, right? So it does know what is the value of every single variable. It knows that x is now half, z1 is 1, z2 is 1, z3 is e, y is 1, right? Since it does know it, it's going to put it on that computation graph. Yeah? Now it wants to compute dy with respect to dz, so it's going to see that this function is 1 over z3. It's going to take this e, which is the value of z3, and put it in that function. It's going to be 1 over e, right? It also knows that this backward function is exponential, so when this value is 1, z2 when it's 1, then this function is going to return the value e, right? So on for the next one, it's going to return 2 because this function is 2z1, and z1 in your computation graph is 1, right? And then the final one is always 2, regardless of what the value of your x is, right? And now, if it wants to compute the derivative of y with respect to x, what it does, it simply multiply everything on the backward pass, right? So you can simply multiply everything on the backward pass. For instance, if you want to know the derivative only with respect to z3, you're going to say it is 1 over e, because the function has given us this output, right? If you want to compute the derivative with respect to z2, you are going to multiply the first one to the second one, and you're going to get 1. If you want to compute the derivative with respect to z1, you multiply the three last guys. And derivative with respect to x is going to be just multiply all of them, which is going to be 4 again, like what you computed on the board, right? So everybody's clear? So this is the idea of backpropagation. The whole reason is because your computer is not able to work with those symbolic operations, right? And not all the time the symbolic operation is very simple. I mean, in this dummy example, I have given you a very specific example, but you can simply think of very complicated function where doing this is not feasible anymore, right? Okay? Everybody's clear? So this is the core idea of the backpropagation, but one thing that is very crucial in the backpropagation is that if your computer wants to compute all of these derivatives, it does need to know the value of every single variable on this computation graph, right? So it means that it has to do forward pass first, right? So you put the input, you see all the values on the graph, and now that you see the values on the graph, you're able to compute the derivatives, right? So if you look at this guy, this diagram here, if you don't know what are x, z1, z2, z3, you're unable to compute any gradient, right? Because those values are important. These are the values which are going inside those partial derivatives or, backward links to compute you the gradient value, right? So this is why we always do the backward pass after we have already done the forward pass. So we go forward on the computation graph, we compute every single variable on this graph, and once we are over, then we can go backward and compute those gradients, right? Using the values we computed in the forward pass. Everybody's clear? Yeah? Great. So that's the key idea of backpropagation. So it's basically nothing but chain rule. And we are going to do it a lot in this course. So you're going to see it like enough number of times so that it's going to get totally convenient for you to do that. Yeah? But if you want to just extend it to the neural network, which is a very massive function, then we really need to extend it to multivariate functions. So this is a kind of multivariate form of the chain rule. So now what you can say for instance, you have one variable yet, so you have only x, and that x is passed through the first function g1, giving you z1, and passed through the second function g2, giving you z2, so on till zn. Okay, so you have n different functions operating on the same variable x, giving you n different outputs. And then you pass those outputs over one multivariate function f, which takes all of those values z, z1 to zn, and compute you y. Okay? Now, if I want to do the same thing we did here, how can I do it? First of all, let's look at the second function, the multivariate function. If I want to compute dy, how can I write it down? Just remember, in the multivariate function, how can I compute the change at the output? The gradient, right. And the gradient contains the partial derivatives, right? So how do I do it? I'm going to compute the partial derivative with respect to the first variable. So the partial derivative of f with respect to z1. And then I multiply it to the change in z1, right? So multiplied with dz1, right? Correct? And then I compute the partial derivative of f with respect to z2 and multiply it with z2 and so on till the very last guy. Correct? You remember that? Which we said this is equivalent to writing the gradient of f. This is a gradient containing all the partial derivatives inner producted with the vector dz, right? Which contains all of those changes inside z, right? So we can write it down in that form. And for every single of those z's, we can say that dz, the change in z, is going to be the derivative of the corresponding function g times the change inside x, right? And then if you just replace it here, so this is the expression, dy is going to be the summation of partial derivative of y, or that function f, with respect to that particular input zn, times the change inside zn. And every single of these zn's, I can simply write it down in this form. So if you just replace it here, then you're going to end up with the vectorized form of the chain rule, which says that if you have a function, in this particular case, if you want to compute the changes inside y, or the derivative of y with respect to x, you can simply compute the partial derivative of y with respect to every single argument inside the immediate function, and then multiply it to the corresponding derivative of that immediate variable with respect to x, right? And then you sum them up, right? So the partial derivative of y with respect to zn, zn is one of those partial immediate variables inside this function. So y is an immediate function of z1 to zn. So you'd compute all of the partial derivatives, and every single of them get multiplied with the corresponding derivative of that z with respect to the x that you are looking for. Everybody's clear? So this is the vectorized form, right? And you can again think of it in the form of a computation graph. So how you can say I have x, and then this x is going to pass through some computation, right? So it's going to get n different computations. The first computation is giving me z1. The second one is giving me z2, and so on till zn. And then all of those computations are getting passed through the function f, and that one is giving me y, right? And then if I want to compute the gradient, or the partial, in this particular case, the derivative of y with respect to x, what should I do? I should just move again backward on this diagram, right? So I'm going to compute the partial derivative of y with respect to z1, right? Partial derivative of y with respect to z2 till zn, right? I'm going to compute all of them. And then every single one is getting multiplied with the corresponding derivative on the previous link, right? So for instance, this f dot, so the partial derivative of y with respect to zn, is going to get multiplied with the derivative of zn with respect to x, right? And so on for the partial derivative of z2, z1, everybody, right? So they are going to get multiplied with the corresponding derivatives. And here at x, you're going to just sum up all of those products, right? And in this guy is going to be your chain rule, exactly the same thing that we had in the previous slide. So, any questions? No?
Are we trying to find like the derivative relative to the weights? Because we are trying to define the derivative relative to the input, right?
To what? Sorry?
We are trying to find the derivative relative to the weights.
To the weights, right?
We are doing.
And x here is our weight, so it's not the x data. Okay, we're not yet there, but we are going to do that. Yeah, but yes, this x is going to be our weight at some point, right? Exactly. That's the idea. So everybody's clear? Okay. So then I have the feeling everybody's feeling asleep. So maybe we can have 5 minutes break, and then we start with this guy, the perceptron. We just use chain rule on that. So 5 minutes. Okay, shall we go on? Great. So now let's see if we can use this chain rule or backpropagation we talked about to compute, for instance, the gradient of the empirical risk, or the sample loss actually in this case, for one simple artificial neuron. Okay? So how does our artificial neuron look like? It's like this, right? So I'm going to get one sample data point, and that sample data point has n different entries. Those entries are going to get multiplied with the weights, added up with a bias. It's going to give me one z. That z is activated by a function. It's going to give me y. And once I have y, I'm going to compare it with a true label v to find out whether this is how different they are. And then I'm going to compute the risk out of it, right? Or the loss out of it, right? So this is the single neuron. And I do assume that I do have the label v. So once I have y, the loss that I want to compute is simply the loss of y minus y and v. For instance, just to avoid any confusion, for instance, you can think of this loss whenever you want. This loss of y and v is simply y minus v squared, for instance, right? This is one loss, correct? This is the square loss we talked about. It could be any other loss. We're going to see more losses later on. But this could be potentially one loss, right? Now, the thing that we want to do at the end of the day is that we want to compute the gradient of this loss. But this gradient is computed with respect to what? With respect to weights, right? So it's going to contain partial derivatives. How many partial derivatives does it have? Number of weights plus 1, which is the bias, right? So you want to compute the partial derivative of that loss with respect to b, w1, w2, till wn. Okay? So we do know how to do it on the computation graph. Can you help me just writing down the computation graph? What is the variable that I should put first in the computation graph? What is it? Is it x? It's the weights, right? So I am not computing the derivative with respect to data. I mean, it doesn't make sense. Data is fixed, right? I am computing the derivative with respect to weight. So here, what do I have? I have the bias, weight 1, weight 2, till weight n, right? These are my variables. These are the things that I want to compute the derivative with respect with. Right? Everybody's clear what I'm doing? Now, these weights, if you fix them, then you can compute the empirical risk. How do you do that? Or the loss. If I fix these weights here and the bias, then the data is fixed because data is given to me, right? So this is the sample data. This is the image that you have. The pixels are fixed, right? And you are going to pass them, once you fix the weights and bias, you're going to pass them forward. You compute z, right? And once you compute a z, you're gonna activate it. You're gonna compute y. And once you have y, you're gonna look at the true label v. You say y minus v squared is the loss, right? Correct? So the output is this particular loss that I want to compute for that set of weights and bias, right? And how do I compute it? Again, you're going to get your bias and the weights, and then you compute z out of it, right? Once you computed z, then how do you compute z? You just simply multiply the bias with 1, which we talked about before, w1 with x1, w2 with x2 till wn, right? And then you sum them up. It's going to be your z value, right? And then the next thing you do, you're going to pass through one function, for instance, ReLU function or step function, whatever, to compute y. And once you have y, then you just simply put it in the expression for loss to compute r hat, right? Correct? Now this is a computation graph, right? I want to compute the derivative of r hat with respect to every single variable I have at the beginning of this graph, right? And how can I do it? I can simply backpropagate, right? But before doing backpropagation, I have to do the forward pass, right? So I had to initially pass my x, or fixing my w's past x. So I set the x here. I just set the w's here. And then I compute everything in between, z and y. And once I have them, now I am able to move backward. Clear? OK. Now, let's just go backward. So if I want to go backward, how can I do this? So once again, I'm just going to compute the derivative, the partial derivatives with respect to weight and bias. And let's try to do it. What should I do first? Any idea? The first step that I should do. I'm going to use chain rule, right? Say I want to compute the derivative of r hat with respect to b. How can I write it down? Can you tell me? If you see it, then everything from now on is going to be super easy for you. If I want to compute the derivative of r hat in this graph with respect to b, how can I write it down? What is this r hat immediate function of? Y, right? Can I compute the derivative of r hat with respect to y? Can you do it for me? Yes or no? Yeah. OK, yes, because you have this loss function, right? You have defined it. If it is this function, then what is this is r hat, right? And then what is the derivative of r hat with respect to y? What is it? 2 times y minus v, right? So I can compute the derivative of r hat with respect to y, right? And now, if I want to compute the derivative of r hat with respect to b, I need to multiply this guy with what? Derivative of y with respect to b, right? Correct? Now, how can I compute derivative of y with respect to b? Look at y. Y is immediate function of what? So, how can I write that down? dy to db, dy to dz, times dz to db. And then, how can I compute dz to db? Partial derivative of z with respect to b, you can simply compute it on this graph, right? What is it on this graph? x0, which is 1, right? This is the dummy input, right? So this guy is, again, partial derivative of z with respect to b. And then this one, based on the graph, is x0, which is 1. And you can do it for w1, w2, every single guy in this graph. So basically what you can say, OK, I am at r hat, and I can move backward to y, because this loss, I have defined it. I do have the derivative, right? I do know what is the immediate derivative. That is easy. Now that I have this, so I have my first loss. I do know the value of y, so I can compute this derivative. And then I can move backward again. I can say, OK, this is the activation function. For instance, it's ReLU function, it's sigmoid function. It's some function that I can compute the derivative. So I do have the derivative. I do know the value of z, so I'm going to put that value of z inside that derivative expression. I have the next derivative, right? I want to get to b because I want to compute the derivative with respect to b. So the next thing is that I move from z to b. And then this is going to be the same thing for w1 till wn. Everybody's clear? OK, so if you put them next to each other, you would say, OK, the derivative with respect to any particular weight, it is going to be the first guy, the derivative with respect to y, which is L dot, times the derivative of y with respect to z, which is F dot, and then finally the derivative of z with respect to that particular weight, which in this particular simple architecture, this is simply xn, right? So now the derivative of your r hat with respect to weight is given in this form, right? And now if you want to have the gradient, you just collect all of them next to each other, right? That's going to be your gradient. So this is going to be your gradient. Your gradient is going to be L dot F dot times x for x0 to xn, right? This is your gradient. You got the idea? Yeah? So now, before I go on, if you are doing gradient descent, what you do? You're going to fix weights, your initial choice of weights, right? You have the weights, then you can move forward, right? You get your y output. You compute the gradient of your output, or the gradient of the loss with respect to those weights. And this is computed at the particular point you started, right? Then you update your weights, right? You're going to say, whatever the previous set of weights was, I get those weights, I subtract the gradient from that. Now I have new weights, right? So I'm going to put new set of weights here. Again, I go forward. When I'm over, I move backward and compute the gradient. Again, update, right? And I keep on going till the gradient is pretty much 0, meaning that the algorithm has converged, right? So every single time you do one step of gradient descent, you are basically going one time forward completely over your neural network and one time backward. And this is, remember, only for one single data point, right? In practice, you don't use one single data point. You use a bunch of data, right? And then you're going to repeat this forward, backward for every single of them. Then you average it, and then you do your gradient descent. We're going to talk about this, but just want to give you the big picture of what we are doing. OK? Everybody's clear? OK. So now that you got the idea, maybe we can go on with a bit of compact representation, because it's going to help us understand how we can write down the backward propagation in a very general MLP. So let's get back to this formulation that we had. So we had these different z values in between, and our x was passed through all of those functions to get z, and then z, those variables z were specifying y. So one thing that I can do, I can just represent these whole links here between x and z in a form of a vector, and call this vector to be a vector z. Okay? So my vector z contains z1, z2 till zn. Okay? And then I think of a general function, which is a vectorized function. It gets 1x, and it gives me n different outputs. It could be, right? It could be a function. And then I show it with this g, boldface, to just indicate this is a vector. And what I can say z is a function of this vectorized function of x using this vectorized function g. And then my computation network again can be shown compactly, right? So x goes through some vectorized function g, and then gives me the vector z, and z passes through another function f, and is giving me y, right? Now, if I want to just compute the derivative of y with respect to x, what I can do, I can just move backward, right? And we did it before. We used that vectorized chain rule. But we can do it, or we can represent it even easier than that. So let me define the derivative of g to be the collection of all of those particular derivatives. Okay? So my function g is getting x, giving me z1, z2 till zn. Then its derivative is simply, again, a vector containing the derivative of z1 with respect to x, z2 with respect to x, and so on, till zn with respect to x. Okay? This is a vectorized derivative, right? And now, if I want to write down the backward propagation, I could say that from y to z, y is a function of z. And since y is a function of a vector, then when I want to move backward, I need to just compute the derivative in a vectorized form, which is gradient, right? Y is a function of lots of variables. Its derivative is basically a gradient, right? So the backward pass is going to have a gradient, right? And then again, from z to x, this is again a vector, a function of variable. Then its derivative is going to be a vector, right? And then I'm going to show it with g dot, right? And if you just write down what we did in the previous slide, so this summation here, you simply can see that this summation is basically the inner product of these two vectorized derivatives, right? So vector form derivatives. Now, what is the moral of the story here? I mean, I do know that you all can do this math, but the point that I want to say is that you don't really need to think about those variables to be single guys, right? So it could be all collected in one vector. Later on, we see a matrix, a tensor, anything. But whatever that guy is, it's giving us something new. And that new thing could be, again, a vector, a variable, a matrix, a tensor, anything, right? But this guy to this guy, when there is a function, there is always a derivative backward, right? And that derivative could be a gradient, it could be a vectorized derivative, it could be a simple derivative, or as you're going to see, it could be, for instance, a Jacobian, right? It could be more complicated form of derivative. But at the end of the day, depending on the dimension of the input and output, you're going to have a form of derivative, right? And if you do know those derivatives, again, backward pass is simple. You just do all of those vectorized form of operation forward, and then when you end it up, you just compute those vectorized form of derivatives and try to multiply them to each other, right? As you can see here, so I don't really need to have that, wide graph anymore. I can just think of x, z, and y as single objects, single components, and then from x, there is one function giving z, and that function has a derivative, right? And again, from z, there is a function giving y, and that function has a derivative. If I have those derivatives, I just multiply them, and this is going to be my overall derivative, right? So the whole story is that we can replace all of those simple derivatives I showed you in the basic computation graph in a vectorized form by just replacing them with gradients or vectorized derivative or whatever it is. Yeah? And at some point in the course, you're going to see it immediately. I mean, you look at the input and output dimension, and you would say, OK, any derivative is, here is a Jacobian, for instance, right? So it's not a big deal for you then. OK? Now, the whole thing, as I told you, backward pass is that you just, first you do the forward pass, you compute everything, and then backward pass is just computation of the derivatives and multiplying them to each other. But the whole tiny detail that is you should pay attention here is that when you are moving backward, then you are multiplying maybe vectors and matrices, maybe vectors and vectors, maybe vectors and numbers, right? So you need to know what kind of multiplication you need to do, right? For instance, here we were doing inner product, right? And this made sense to us because y is a single number, x is a single number. The derivative should be a single number, right? When I have two different vectors and I want to just produce one number, what do? I just do the inner product, right? So I need to just find that out. So how can I do this? For instance, here, as I said, we did the inner product. I just need to know what is the right choice of the product. And once you know it, then the whole backward propagation is exactly the thing we did with the basic chain rule. OK? Any questions? No questions? OK. Let me just try it for the single neuron that we did. Let's look back at the single neuron that we did right now. So for that one, we computed the derivative of the empirical risk, the loss, with respect to every single weight, right? And then I could essentially collect everything here within one single vector. What could I say? I could say that, OK, my data, x0 is the first entry inside the data, x1 is the second one, x2, and so on till the last one, right? And I could write down x, this vector, this is a vector now, which contains all of those single entries inside my data. This is the whole sample that I have as the data inside my data set, right? And now, I can also collect all of the weights within one vector. So I have one vector. The first guy is the bias. The second one is the first weight, second weight, and so on till the last one. And what is this operation here? What do I do to these weights and this x to compute z? It's an inner product, right? So I could simply write down z to be an inner product of x and w. And I don't need to have all of those branches in my computation graph anymore. The only thing that I need to do, I can just draw this compact computation graph, right? I would say I have a vector. This is not a number anymore. It's a vector. But it's an object, right? It's very good if you start to have this feeling about those numbers, right? So it's not a number. It's an object. It's a part of the memory of your computer, right? It could be one variable. It could be a bunch of variables. Doesn't matter. And you don't really care how they are sorted out, right? Because at the end of the day, you can fix it in a way that you can just multiply it to something else, right? So this is one object. This is in the form of a vector. And this vector is getting multiplied with another vector, producing one number for you. So it's essentially an inner product, right? So you do the inner product. And then once you have this variable, anything else is a scalar. So you get this variable. You do one activation. And out of the activated version, you compute the risk, right? And if you want to just do backpropagation, then you simply say that r hat is a function of y. This is a scalar. This is a scalar. So the derivative is going to be in a scalar, right? And it's going to be L dot. So I can simply do that. Then I would say z is a scalar. Y is a scalar. They are related with a function. So the derivative is, again, the derivative of that function f, which is in a scalar, right? So that one is, again, easy. But now, what about z and w? Z is a scalar, right? W is a vector. Now, if I want to compute the derivative, what kind of derivative is it? A variable is a function of a vector. Then it's going to have lots of partial derivatives, and I can collect all of them into a form of gradient, right? So a scalar function of vector, then when you want to just compute the gradient, the derivative, it's going to be a gradient, right? So next thing, you would say z is a scalar, w is a vector, and then I'm going to have a gradient of z, right? And that gradient of z contains all the partial derivatives of z with respect to weights, right? And then you can put it inside a vector. And now you just need to do backpropagation in this form. So one scalar multiplied with the second scalar multiplied by a vector, and bingo, you have the gradient, right? So you're going to get a vector, right? And that vector is exactly the gradient that you want, right? So this L dot is easy. You do know it. We did it on the board, right? That F dot is, again, easy because you fixed the activation function, right? So you can compute that. What about this gradient? OK. Z is given in this form, x transpose w. So I can simply write it down. Z is x inner product of my weights and my x, right? Correct? Now, if I want to compute the gradient of z, how can I do it? I'm going to say that the gradient of z contains, the first entry is the partial derivative with respect to w0, right? So it's going to be partial derivative with respect to w0. The second one is partial derivative with respect to w1, w2, and so on till wn, right? What is the partial derivative with respect to w0? 1. What about w1? w2? And so on. So it's basically the vector x itself, right? So if I do know that the partial, this one you can always compute, right? Because you know z is inner product of x and w, then you can do exactly the same thing to conclude that gradient of z is x itself, right? And now that you have this, then you replace here instead of the gradient x. Clear? Again, you have your data, you fix x, weight is initialized, so you go forward, you compute y, then you compute all of these derivatives. X is fixed. You can compute this one as well, right? And then you get your first derivative, right? Correct? First gradient. You subtract from the weight. You get a new weight. You put it here. Again, you go forward, backward. New weight, forward, backward. New weight, and so on till the gradient is 0, right? And then you stop. Everybody's clear? So, moral of the story, whenever you do the backward propagation, you basically, I am just repeating the same thing I said. You basically need to just write it down in form of a computation graph, and you can always write down those backward links by looking at the objects that you are getting connected, right? So when two objects are, if a vector is connected to a scalar, then I should go back with a gradient. If a scalar is connected to a scalar, then I should go back with a derivative of a scalar, and so on, right? And then you can do the backward propagation. So you would say the derivative of r hat with respect to weight, I'm going to start with the first immediate variable y, and then after that I just go for the next immediate variable z, and so on till I get to the very last variable w, which I am looking for, right? And then I'm going to get the right gradient, right? And then I keep on updating till it's over. Any questions? Everybody's clear on the backpropagation? Yeah? So this guy now sounds easier as compared to the case where I think of that y, or that empirical risk, to be a very complicated function of all of the weights, and then I want to compute the partial derivative with respect to every single of them, right? Because this is giving me a kind of algorithmic approach to compute all of those gradients that I want, right? And you might think that I'm going to stop here and I'm going to say, okay, that was backpropagation, let's go to the next topic, right? But you are totally wrong, because this whole course is about backpropagation. We are going to do it for different architecture. First one, MLP, okay? So now that we have done this, we are going to just try this idea on one MLP. So for us, MLP, you remember that compact form I showed you? I'm going to show you again. That I start with 1x and then pass through a matrix, activated the next hidden variable, and again, linear transform, activate, and so on. That was somehow our computation graph, right? We need to do a bit of modification, because we don't look for x, we are looking for the weights, right? But once we do that, then we have the computation graph, and we want to apply the same idea on that computation graph. And you're going to see that this is basically just linear operations. And this is why all of those neural networks nowadays are getting trained. Yeah? Okay? So, before going on with that, I am going to do you 3 major local operations. And don't get confused, we are not yet doing any backpropagation on any neural network. Okay? I am just doing chain rule again for 3 basic operations. And once you know these 3 basic operations, you basically can immediately backpropagate over a MLP. Okay? Any questions? Everybody's clear? So by the way, this idea of backpropagation was something people did not buy it. I am telling you now, and I see this in your face, that you don't buy it. Say it's a very deep neural network, so you're going to move backward and do all of those products. People did not buy it. They said, like, it's not working. And actually, AlexNet, the whole winning point of the idea was that it just proved that backpropagation is working, right? So there were few people who believed on backpropagation. Now there are lots of believers, right? So initially, people did not believe that it's going to work, but apparently, those people who were consistent could prove that they are wrong. Okay? So let's start with these local operations. So as I told you, I am not yet doing anything on a neural network, so don't get confused. This y, z, whatever you see here is not yet on the neural network. We're going to take it on the neural network later. Okay? So what I'm going to do, I am assuming that I have one objective, so r hat. R hat in your neural network is the empirical risk, yeah, or the loss. But right now, you think of it as a function, okay? So r hat is a function of one vector or one object, y, okay? And what I do know about that is that I do know what is the gradient of r hat with respect to y. Somebody told me. Somebody told me that the partial derivative of r hat with respect to the first entry inside y is partial derivative of r hat with respect to y1. For the next second entry is with respect this, for the third entry is that, and so on till the last one. So somebody has given me this gradient, this vector here, and now what I want to do, I do know that there exists one other variable which could be, again, an object. So it could be a vector, it could be a number, it could be a matrix, it could be anything, okay? And that variable is connected to y with some operation, yeah? So there is this particular red node. This is one variable. It could contain any mathematical object. And that thing is connected by one function to y. So y is an immediate function of this guy, right? And what I do now is the gradient of r hat, the final output, with respect to y. Now what I want to do, I want to use the chain rule, use the same backpropagation we did here, to find out how I can now compute the gradient of the final output with respect to z. The red guy, the red variable. Okay? So, meaning that starting from r hat, I have backpropagated up to y. Now I want to do one step further. Okay? I want to get to the red node. Everybody's clear what I'm doing? Again, this is not necessarily a neural network. It's a general thing. Yeah? So those links could be any functions, and I do know what those functions are. Okay? Okay. So let's start with the first local operation. So I'm going to solve 3 of that, and for each of them, I think of one specific variable here and one specific function here, and I try to do that. Once you get those 3 operations, then you can backpropagate over one MLP. So let's start with a very simple one. So the first one is entry-wise functional operation. So what I assume that this y, so once again, I do have this gradient, the gradient of r hat with respect to y. I do have it. Now, what I do know is that this y is given by other function, by other variable z. So y is a vector, z is a vector as well. Y has k different, I don't know, it's k different entries. Z has also k different entries. And every single entry in y is computed by one function from the corresponding entry in z. Like y1 is f of z1, y2 is f of z2, and so on till the last one. Okay? Do we do this in neural networks? Yes. When do we do that? When we do activation, right? So we compute z, and then out of z, we just activate it by some activation function. And the activation function operates entry-wise, right? So you can think of that. But again, we are not yet there. Okay? It's just you think of one variable z. You have this entry-wise operation. You get the vector y. And then you do know what is the gradient of very output with respect to y. Okay? Everybody's clear? Okay. Now what I want to compute, I basically want to compute the gradient of r hat with respect to this z. Okay? Now, let's just open it up. So I want to compute the gradient. First of all, this gradient, I told you that y has k different entries. You see it here? Now, how many entries does the gradient have? K, right? Now, what about the next derivative that I compute? What kind of derivative is the derivative of r hat with respect to z? It's again a gradient, right? What is the dimension of that gradient? So z, I told you again that is k-dimensional. So what is the dimension of that gradient? That's again k, right? So I'm going to start with this k-dimensional vector. So this guy is k-dimensional. And after doing the backward propagation, I should end up with, again, a k-dimensional vector, right? So I want that. Now, let's do it. So every single entry inside this gradient of r hat with respect to z is going to be something like this, right? So it's going to be a partial derivative of r hat with respect to one of those entries inside z, correct? Now, how can I write it down? I can use chain rule. I can say this is the partial derivative of r hat with respect to y times partial derivative of y with respect to z, right? Should I do it by summation or not? Let me just write it down on the board for you. I hope that I have a board left. No, I don't have. here. Don't look at that slide, just tell me this. This r hat is a function of what? R hat is a function of y, meaning that r hat is a function of y1, y2 till yk, right? All of entries of y, right? So if I want to be fair and write the chain rule properly, I am going to say that partial derivative of r hat with respect to one particular z, say for example with respect to z1. How should I write it down? I should write it down as the partial derivative of r hat with respect to y1 times partial derivative of y1 with respect to z1. Should I stop? Should I? No, because there's y2 also here, right? So it's going to be partial derivative of r hat with respect to y2 times partial derivative of y2 with respect to z1. Great. And so on. But I didn't write these terms for you. Why? y2 is not a function of z1, right? So what is this derivative? It's 0. What about the next one? 0, and so on, right? So if I'm looking only at zk, then it's going to be impacting only yk, right? Because we said this is entry-wise function, correct? So this is why I have written the chain rule in this form. And then what is this guy is the partial derivative. I do have it inside my gradient. What about the partial derivative of yk with respect to zk? What is that? I do know f. I just compute the derivative of f, right? At point zk, correct? So this is going to be f dot zk. And then I could say that every single, so if I just collect all of them inside one gradient, then every single entry of that gradient with respect to z is going to be the corresponding entry of the gradient with respect to y times f dot at point z, right? This is what I show it in this form. And by this dot here, I simply mean entry-wise product. Okay? So I basically mean that. So z entry-wise product y, it simply means, okay, an equality sign is missed here. So equals to z1 till zk times y1 till yk. So it's going to be y1, z1, y2, z2, and so on till the last one, right? So k dimension times k dimension going to give you k dimension. Right? Everybody's clear? So, moral of the story, if there is one entry-wise operation here, then once I want to move backward, meaning that I want to compute the gradient of r hat with respect to z, the only thing that I need to do is to apply the derivative of that function on z, so it's going to be f dot z, and do this entry-wise operation on two gradients, right? Or two vectors, okay? Now, one thing, z is k-dimensional, right? The kind of derivative I would get here is k-dimensional. Here again I have a k-dimensional vector, right? And at the end of the day I want to end up with a k-dimensional gradient. So k-dimensional, k-dimensional, ending up k-dimensional. The best kind of multiplication that I can think of is entry-wise product, right? Because two k-dimensionals should end up to be k-dimensional, right? So you don't really need to do all of those chain rules I did here. You always think of it like that. Yeah? Z is a vector, y is a vector. Both of them have the same dimensional gradient, so the corresponding thing should be this entry-wise product, the kind of product I'm going to use here. Okay? Now, next thing. The next thing that I'm going to consider, again, I consider the y, the gradient of r hat with respect to y is given to me. But now, I don't think of this simple entry-wise function anymore. I think that there exists one z, and this z in general could be different in dimension. So you see here, z could be n-dimensional, and y is k-dimensional. So it could be different. And I have one matrix A, which is getting multiplied to Z, giving me Y. Okay? So first of all, what is the dimension of that A? What is the dimension of A? Y equals AZ, okay? This guy is k-dimensional. Sorry, n-dimensional. N. This guy is k-dimensional. What should be the dimension of this one? K by n, right? So this guy should be k by n, right? So now I have computed those gradients for you inside this slide. And you can go ahead and check it out, but I don't want to tire you with that. So let's try my trick that I told you. So the gradient of r hat with respect to y, what is the dimension of this guy? Look at it. Y is k-dimensional. What is that gradient in dimension? K, right? Now, what about z? The gradient of r hat with respect to z. What is this guy? N-dimensional, right? Now, forget about the fact that y, z, and a are matrices and vectors. Think of them as scalars. If y equals by az, then what is the derivative of y with respect to z? It's a, right? So a is your derivative, correct? So that link from y to z should be somehow proportional to a, right? So let me be dummy and write this guy down for you. So I'm going to write this guy a here, okay? And now, does it work? Can I multiply a with this guy? Look at the dimension of A. A is k by n, right? Can I multiply by a k-dimensional vector? No. What should I do to that to be able to multiply it? Transpose it. I just replaced transpose here. Okay. Can I do the product now? Yes? Yes or no? Yes. Okay. Now, if I do the product, then the output, what is the dimension? This A transpose is n by k now, right? Multiplied by k-dimensional vector. Going to give me n-dimensional vector. It sounds to work, right? And then if you go ahead and do all of those calculations, you're going to end up seeing that, yes, the derivative with respect to z is A transpose derivative with respect to y. Okay? So you can go ahead, check it if you don't buy my words now. But trust me, I have done it a couple of times. I mean, it's a long time I'm teaching this. Okay? So it's very hard that I'm doing any mistake on that. So this A transpose is correct. And you can always do it using the idea I told you. So you just think of this operation here from z to y. It's a linear. So the derivative of a linear is simply the coefficient, right? And then you just need to find out the right kind of product that you should do in order to make these dimensions to match, right? So moral of the story, the derivative of z in this case is simply A transpose the gradient. And as I told you, so I think I have written it here exactly. So since we are changing from with m, I mean m is missing, k to n, then just to make the dimensionality fit, you just need to replace A with A transpose. Okay? Now, last thing. I have A here, and A is getting multiplied to x. Now, my variable is now A. Okay? So A is the guy who I can change, and x is fixed. A is getting multiplied to x, one vector, and it's giving me one vector, y. Okay? And out of that y, I am computing r hat. And I do know the gradient of r hat with respect to y. I now want to compute the gradient of r hat with respect to A. Everybody's happy with gradient with respect to a matrix? Do you have the idea how I can extend the gradient to a matrix argument? What do we do when we have a vector? If it's an n-dimensional vector, I'm going to compute all of partial derivatives and put it in the place of the variables, right? Now that I have a matrix, how many of those partial derivatives I do have? As much as entries I have inside my matrix. I can compute every single of them and put it inside the matrix. So say that your matrix is, having k rows and n different columns. So for every single a, k, n, every single entry inside that, you're going to have one partial derivative. So you compute that and put it inside a matrix. You're again going to have one matrix of the same dimension, and that is now your gradient, right? So everybody's now happy, right? Clear? So now let's get back to the question that we have. Okay, this is just one extra argument that I put here. So if you think of optimizing in terms of A, basically what you're going to do, if you are doing gradient descent, you just start with 1A, you compute the gradient with respect to A, subtract it, and you keep on doing it. So you can always think of any mathematical object inside your gradient descent, inside your backpropagation. I am just doing my best to just transfer this idea to you so that you're going to feel comfortable for the rest of the semester. But anyways, let's get back to our question. And our question is here. And again, I'm not going to take all of those, detailed derivations. I want to use my trick because that's going to be much easier. Okay? Now, the thing that I want to compute the gradient with respect with, so here, so I have my matrix A, and this matrix A is getting multiplied to X to give me Y. Okay? Now, this Y, I think in the question or in the problem we have it k-dimensional, right? This is k-dimensional. Okay? And this vector here, x, is n-dimensional. Now, the dimension of A is obviously k by n, right? K by n getting multiplied with n-dimensional going to give me k-dimensional, right? Now, one thing that I do have the gradient of r hat with respect to y. What I'm looking for gradient of r hat with respect to A. Now, I need to just put something here, okay? Now, let's check the dimension. What is the dimension of this guy? Great. What is the dimension of this guy? K by n. Okay? Now, again, y equals by A times x, yeah? Think of A, x, and y to be scalars, yeah? If y equals by A times x, then what is the derivative of y with respect to A? X, right? So x is the guy who contains the derivative, right? Correct? Now, I want to replace x here, okay? But if I replace x, what is the dimension of x? N, right? So I have n-dimensional vector. I have k-dimensional vector. I want to do a product such that I end up with a k times n matrix. How can I do it? Do you remember any form of product of two vectors which give me outer product? Great. Yeah? So if I do the outer product of a k-dimensional by n-dimensional, I'm going to end up by a k times n matrix, right? So I can just take this x and do the outer product. So I'm going to put here, so this is k-dimensional, k by 1. And then I put x transpose here. And then this guy is going to be a row vector n-dimensional. This is a column vector k-dimensional. When I multiply them, I'm going to end up with k by n matrix, right? Sounds it works, right? You see it? Everybody's clear? So, you got a question? So, if you go ahead and do all of these calculations I did here for you, then you're going to end up at the end with this expression, which is exactly that outer product I showed you. Okay? So, moral of the story again, this makes sense again for you, because that gradient should be a matrix k by n. You have two different gradients. One of them is k-dimensional, one of them is n-dimensional vector. You just compute the outer product, you're going to end up with the gradient that you want. Okay? And this is going to be the moral of the story. So you start with r, then you compute the gradient with respect to y, so you have it now. Now if you want to backpropagate to a, you basically get this one and outer product it by x, and then you're going to have the gradient with respect to x. Everybody's clear? Any questions? No questions? Okay, great. So if you got no question, then if we use these three different operations, then we basically can compute the gradient with respect to any weight matrix inside or MLP. And I'm going to show you this next Tuesday. Okay? So you're going to see that when you have this architecture, you can always think of it to be a kind of computation graph. And if you want to compute the derivative with respect to one particular weight matrix, you're going to put this weight matrix at the beginning, so you cut your graph at that point. And then you're going to replace it something like this. So we're going to have this particular computation graph. And then we backpropagate over this to get the gradient with respect to that weight. We have it. We keep on going. We just do it to get the gradient with respect to all of those weight matrices. That's over. You have all the gradients. And the only thing remains is that you go forward, backward with these two algorithms. Compute gradient, update your weight, again forward, backward, and keep on going till your algorithm converges. So, any questions? Everybody's happy with the backpropagation? Yeah? So may I see you on Tuesday? You don't see like people who show up on Tuesday. Yeah. But for Tuesday, please just have it. I tried to review it, but have it in mind, the three main operations, so that we can simply do the backpropagation. And you're going to see the algorithm by your own eyes. And then that's it. Okay? Okay. Great. See you on Tuesday.